Now we can see for ourselves what exponential growth looks like by doing a little experiment. And if we can bring one of the handheld cameras in, we can have a look at this. So in this box, I have 225 armed mouse traps. And on each mouse trap, we have a ping pong ball. Now in a moment, we're going to take one more ping pong ball and we're going to drop it in through this hole in the top. And it's going to set off a chain reaction. And in this chain reaction, the number of ping pong balls flying through the air is going to grow exponentially. Okay, so who would like to volunteer to come and set this off? My goodness. Let's have you there. Yep. Yes, you'd like to make your way along the end of the road. If you'd like to come and stand just there, and just turn that way. Okay, that's good. And what's your name?
Matthew.
Matthew, you'd like to hold that. Now, in a moment, we're going to give you a 3, 2, 1 countdown. Okay. When we get to go, all I want you to do is to place the ball in through that little hole at the top. You manage that? Yeah.
Yep.
Okay. Are we ready? 3, 2, 1, go! Amazing, excellent. Okay, thank you very much. Okay, so we have a high-speed camera that was looking at that, and perhaps we can just do a little action replay and see that in slow motion. So there's the first ball, setting off a couple more. Each of those is setting off several more. And on that curve, we can see the number of balls growing in this very dramatic way. And what's really impressive about exponential growth is that the rate of growth is itself growing exponentially.
If you were listening, you saw that this case started with 225 ping pong balls. Matthew initiated the reaction with 1 ping pong ball, for a total of 226 in that case. If that initial ping pong ball sets off another ball, and they each set off another, and each of those sets off another, we can fill in the number of active ping pong balls at each time in this chart. At time 0, that initial reaction, Matthew starts with 1 ping pong ball. If that sets off another, we have a total of 2 active ping pong balls. If those each set off another, we have a total of 4 active ping pong balls. If those each set off another, we have a total of 8. And if those set off another, we have a total of 16. You can see the pattern developing here, where each step is just a multiple of 2. So times 2, times 2, times 2, times 2. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. Theoretically then, at time 4, we would have 256 active ping pong balls. However, since this is a real-life situation, this function maxes out at 226 because there's only 226 ping pong balls in that case. Take a second to graph the data on the grid below. The scatter plot you have should look a little something like this. If you connect these points, you see an exponential function that looks like this. Using your mathematical knowledge, you know that this line will never reach the x-axis. That makes the x-axis an asymptote for this function. The domain, then, of this function, p of t, represents the x values. You ask yourself, what's the smallest that x can be? This line will extend forever to the left, so negative infinity is the smallest x, and likewise positive infinity is the largest. As far as the range, you look at the y values. There is no y value below that line of 0 because that, again, is an asymptote. So the range, or the y values, go from 0 to positive infinity. The y-intercept of this graph, it's hard to tell, but that point you plotted was the point 0, 1. And lastly, that asymptote of P of t. It's a horizontal asymptote, which makes it a y equals line at the line y equals 0.
What's better, faster or slower?
Faster!
Okay, what's fast?
My mom's car and a cheetah.
Okay.
A spaceship.
Spaceship. And what's slow?
My grandma's slow.
Would you like her better if she was fast?
I bet she would like it if she was fast.
Maybe give her some turbo boosters.
Tape a cheetah to her back.
Tape a cheetah to her back. Seems like you've thought about this before.
It's not complicated. Faster is better. An iPhone 5 downloads fastest on AT&T 4G.
Here is your new friend E. What is E? E is such a special number that it's given a name, or more specifically, a letter, E. E is approximated at 2.718281, blah, 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 and so on. This E is an irrational number, but I'll be happy if you can remember that it's about 2.72. If you're calculating with E, you should use the button on the calculator that is second ln. If you just want E to the first power, you can type this button E. A box appears, and in that box, you'll just put a 1, because E to the first power is E. If you're trying to calculate E squared, you can type this E, and in the box, type a 2. If you're trying to calculate E to the negative 3, you can type this E, and in the box, throw a negative 3. Use this to graph e to the x and its inverse, as well as their domain, range, and asymptote.